Okay, welcome to the CAP seminar. Today it's my pleasure to introduce our very own Professor Shen. He's going to be talking about AGN with Sloan 5.
Okay, everyone, since nobody's taking the front seats, so I'm standing here in the solitary to talk to you. People on the Zoom, can you hear me okay? I have no idea your response.
Yes.
Okay, great. Let's talk about quasar science in SDSS-V. Although I should warn you that this is not a very well-polished talk. like half an hour to prepare for it. But I do want to, since a large part of the effort is being carried out here at Illinois, I do want to introduce to you some of the basic information and also showcase some efforts that are being done by Illinois students, postdocs, and research staff. All right, so let's get started. So what is SDSS-V? So we all know about the Sloan Digital Sky Survey. And it started around 2000. And now it's the 5th generation of the Sloan Digital Sky Survey with small telescopes. So SDSS-V, in a nutshell, it is a 5-year or actually 6-year survey that will monitor the entire sky with multi-epoch spectroscopy, both in the optical wavelengths and also in the infrared wavelengths. That's the, when we say near-infrared wavelengths, it's actually just H-band, not GHK. But it's H-band spectroscopy. So in science, it features 3 mappers. The Milky Way Mapper, which is kind of the flagship program of this Sloan 5 survey, intends to study the evolution of the Milky Way and to understand the genesis of elements in the Milky Way galaxy, the physics of the stars and interstellar medium, as well as the architecture of multiple stars, as well as exoplanets. The black hole mapper, which is something that I'm particularly interested in, will study the growth of supermassive black holes through the cosmic history by observing quasars and active galactic nuclei. A small part of the BHM program will also target cluster galaxies. Okay. By the way, you should interrupt me freely, and we can engage in more interactive discussions. And the final mapper is called the local volume mapper. So this is a very large IFU survey. It builds new instrument IFUs and to observe the Milky Way in the integral field spectroscopy, to study the ISM and stellar populations, but also some observations of the local group of galaxies. So you might be asking, so it's already 20 years since the first SDSS. What's new? Right? What new can be done with this 2.5 meter telescope? Well, there are a couple of aspects that I think are unique to Sloan 5. One is that now we have expanded the territory into the southern hemisphere. So now, in addition to the original 2.5 meter Sloan telescope at Apache Point Observatory in New Mexico, they also have a second 2.5 meter telescope. That's the DuPont telescope at the Las Campanas Observatory down in Chile, to give you southern sky coverage. And you know, it's better to observe the Milky Way from the south. And the local volume mapper actually builds new small, or actually use new small, smaller telescopes and to put their very large field of view IFU units there on those smaller telescopes. So the second unique aspect of SDSS-V is that it's multi-epoch. That is, it's a time domain spectroscopic experiment. Then we're going to revisit the same part of the sky over and over to build light curves, spectroscopic light curves, to study persistently variable sources in the universe. Okay. So back a few years ago, when the SDSS-V project was announced, in the summary paper by the director, Coleman et al., it was a comparison of the multiplex spectroscopic surveys in the 2020 to 2025 period. So Sloan 5 is at the top, and this is the number of multiplicity of spectroscopy, wavelength coverage, sky coverage, number of epochs, and the duration of those surveys. And as you can see, a lot of those surveys have been significantly delayed. As you know, some surveys are supposed to be ending now, but they haven't started yet. So in that sense, SDSS-V was also delayed, significantly. But at least we're taking data now, and hope time frame will be through 2020, 2025. All right, let's see. So, yeah.
Is every component taking data now, or just some?
For SDSS-V.
Yeah.
So Milky Way Mapper, Black Hole Mapper, they are both taking data. The local volume mapper just had a milestone of building the instrument. So they're supposed to start next spring.
But the 2.5 meter going, they're operating.
I'll get to that. The APO 2.5 meter is ongoing. The DuPont 2.5 meter is commissioning.
Gotcha.
So says that 4 pi and then MH less than 13.4. Like, do you basically have a spectra of every star greater than 13.4?
The number of epochs varies greatly among different targets. So for those bright stars observed with the H-band spectroscopy, most of them are not multi-epoch.
Okay.
So just get one epoch, one 50-minute exposure.
Spectrum for every 13.4 greater star?
Most of them, I wouldn't say every of them, because it has to be within the area, a targeting area. But there are lots of them selected from Gaia, where they have additional information for the stellar populations.
So 4 pi doesn't mean 4 pi?
That's correct.
Okay.
So it's roughly 4 pi. The total area coverage, combining both telescopes, is roughly 4 pi. But those specific targets, like for example, disk stars, that's not 4 pi. Halo stars, potentially 4 pi, but not sure they're going to point in every direction in the halo. And 4 pi also means that for a lot of those things, they are actually kinetic sources, like quasars, AGNs. So it's really 4 pi means that for every point in the sky we're going to visit, except we don't know how many targets are there and how many times we're going to visit that point. So what is Illinois' involvement? So we are an associate member institution, which grants us a seat of, on the advisory committee, so we have voting rights. This associate member comes with 3 faculty slots, and that's Tony Wang, Shen Liu, and myself. So the participation, the buy-in was through in-kind contribution. It's roughly equivalent to $500,000 for the entire period of the survey. The in-kind contribution is mostly one full-time research scientist, that's Sean Morrison, to take charge of the optical spectroscopy pipeline. So that's the one of the 2 multi-object spectroscopy components that we are responsible for to reduce the data, calibrate the data, and also coordinate with the survey teams. And plus my additional contribution to the overall management of the project. All right, so the BHM I'm going to talk about the science you can do with Black Hole Mapper. This is the primary dark time component of SDSS-V, because for H-band spectroscopy, they use a lot of bright time. But we have to do it mostly in dark and gray time. So the optical spectroscopy is largely the same as previous generations of SDSS, except that we don't use plates anymore. So for previous generations of Sloan, the multi-object target spectroscopy is taken by drill holes on aluminum plates, and which is mounted to the back of the telescope. But now, because we need a rapid slew of the telescope to take very efficient coverage of the large chunk of the sky, plates production is very ineffective. Is not cost-effective in that sense. So we're going to use robots to rapidly reposition those fibers when we slew from fields to fields. Because of that hardware change, previously we had 1,000 fibers, 1,000 objects observed simultaneously in Sloan 3 and Sloan 4. And that's come from a pair of identical spectrographs. But now we have split these two spectrographs. One stays at APO, and the other one shifted to Chile. That means for each field, now you only have 500 fibers, 500 objects simultaneously. The 300 of those 500 actually has the robots there, actually controls both fibers. So it can either be used for the optical fiber, but also for the apogee H-band near-infrared fiber. And the field of view is kind of smaller than the nominal 7 square degree field of view that some of you might be familiar with from previous generation of Sloan. Now we're down to 6.5 square degree at APO, and at LCO, it's a huge reduction. Now we only have 2.7 square degree at LCO, given the different plate scale and configurations of the LCO telescope. But the spatial resolution and fiber size, etc., those are still matched such that the still medium resolution spectroscopy in the optical from both APO and from LCO sites. On the right, I just show the focal plane layout of all those fibers, and the back end of that are 500 robots. And it's a hexagon design. And there are some central holes that we cannot patrol the robots there, and some fiducial holes have to drill to configure this pointing. So science. BHM will have 3 components. So there are 3 mappers, and for BHM there are 3 components. So it will observe use 2 hallmark characteristics of quasars. And one is the copious X-ray emission from accreting supermassive black holes, and the other is the ubiquitous UV optical variability you observe in the spectrum of quasars. So in this cartoon figure, I illustrated the 3 components. The central is the accreting supermassive black hole surrounded by a compact, very hot corona of relativistic electrons, emits in hot X-rays, and then a few gravitational radii all the way to maybe thousands or even tens of thousands of gravitational radii. You have this relatively cooler accretion disk, still pretty hot, but cooler than the X-ray corona, that gives you the UV optical emission of quasars. And then a little bit further out, you have gas clouds, those are broad emission line regions, to produce those very strong and prominent broad emission lines in the spectrum of quasars. It's interesting to note that the timescales associated with these compact regions are very short. So the light crossing time range from much less than a day, we're talking about seconds if it's a X-ray corona, to tens of days in the broad line region. for a typical quasar at redshift 2. And the dynamical time scale, think of this as the orbital time around the black hole, is longer, but still we're talking about several years in the borderline region. Kind of measure the time scale duration of the Sloan 5 survey because we want to measure changes in the dynamical state of the borderline region around those supermassive black holes. So the X-ray component is basically spectroscopic follow-up of eROSITA AGNs. Well, eROSITA X-ray sources, but most of them are X-ray AGNs. Some of them are stellar objects like X-ray binaries and cataclysmic variables, and also galaxy clusters that are also extended X-ray sources. So the baseline plan is to observe 300,000 eROSITA X-ray sources to provide classification, redshift measurements, and also physical properties measured from optical spectroscopy.
And has that plan changed given eROSITA?
I'll mention that later.
Okay. And at some point, I would like to ask, are there opportunities to make sure, how do we check what targets are? I would like to know if all the SPT quasars in the south are already on your list. How do we?
All right, so let's, that's a perfect point to have a break and discuss here. So there will be calls for ancillary targets. In fact, there was already one call for proposals for ancillary targets that participating members can propose so-called filler targets to use unallocated fibers. Now, this procedure has been slow and also chaotic because of the complications of merging all those different observing components and some delays as well. But the first round of ancillary targets were put in. Now, there will be future calls, at which point, if you find some interesting targets that are missing from the already observed, already compiled target list, then through collaboration, you can, if you're a member, then you can propose.
We are a member here, right?
Associate member, that doesn't cover everybody. If you have an extra $500,000, we can upgrade to a full member.
But if I gave you a list, that would be fine.
It will be fine for me.
Yeah.
But I'm not obligated to give you back the data. So the idea works that way. I have to go through the so-called external collaborator status. That is, I can be the champion to sponsor this external collaborator and I say, this is a great opportunity to follow up those blazars, SPT blazars. And as part of the deal, you, Joaquin, and key members from SPT can have data access right. And in return, SDSS members can sign up on this paper. So it has to be go through that external collaborator status. A little bit lengthy, but doable.
But isn't ultimately everything becomes public, right?
Everything becomes public, but the targets are not every target. There's so many targets to choose from. So I'm sure that some of your blazars are already overlapping with eROSITA X-rays sources, so they will be already be there. And they're going to publish their targets, not the actual data, but the targets shortly. So you can cross-check with their published target list to know if this object is already covered or planned to be observed by Sloan 5. Okay. If not, then you can propose an additional set of ancillary targets.
Okay, so you have a list now of what's going to be targeted?
Yeah, okay. For X-rays, for eROSITA, right, and for other components, right? Yeah, the target selection is evolving, but we now have a baseline plan for the target samples. Yeah.
So related to all of this, do you have?
It's okay. Yeah. So he was first.
That's fine.
But you're his boss, right?
Okay. So you have 500 fibers. Presumably, some of them are always free, even when you have a field with a whole bunch of targets. Is there a plan to do TAO observations that are just made public? And how
That's a great
quickly,
question. Something that I have been twisting their arms to do. And got cold water like every time. The problem is that scheduling is gonna create holes. Not actual holes. Create complications in the plan. Something that the survey planning team does not want to get involved right now. But once the survey becomes a routine, all the commission issues are solved, then I'm gonna bring this up again. I know DESI has been doing similar things.
And
right?
we proposed to DESI that we will feed them targets from YISI and other surveys that Illinois is part of.
Yeah.
And I'm happy to come give that spiel to SDSS.
Yeah, I think it's doable. We can have a dynamical evolving target list for TO target list, and just insert those design files that we have. In addition to X-rays, we have reverberation mapping. That's to map the geometry and size of the broader region around creating massive black holes. And that's a project that I'm one of the leaders here. And finally, the other time domain spectroscopic component is to observe 25,000 quasars with a few epochs across the 5 years. Some of them will be observed by up to 12 epochs. And in combination with spectroscopy taken like decades ago, we can observe radical changes in the appearance of those AGN quasars. And some of them are known as changing low quasars. Object apparently changed from type 1 broadline AGN to type 2 AGN and vice versa. Okay? So this few epoch spectroscopy program will observe a large number of those radically changing accreting supermassive black holes on the dynamical time scale of the accretion disk and broadline region. All right, so this is the first all-sky image from the eROSITA survey when they made their first press release. And it's quite impressive. If you compare this with the ROSAT, then you are seeing much finer details of the diffuse emission of the sky and also the individual point sources from the X-ray detection. The Russian side and the German side, they kind of put together to this sky figure. As some of you might know, that this is eROSITA X-ray mission is a partnership mainly between German and the Russian. The way that they collaborate is that they divide the sky into two halves. The Germans take one half, and the Russians take the other half. So the Germans can do the science in their half of the sky and propose targets through SDSS-V, and the Russians do their follow-up with other surveys and the facilities. Okay, and yeah.
My question was exactly about this. So do you collaborate with the Germans? So it is Southern Galactic Hemisphere?
They have a galactic longitude division, I think. They have a...
Remember, they split by, so Northern Galactic Hemisphere is Russian and Southern is German, and galactic plane is common, right?
I thought they traded Cosmos for the Black Center somehow.
Yeah, so I think, German gets the galactic center, but the simple cut the sky is a galactic longitude, I think.
Yeah.
Which cuts the galactic center in half.
Okay, I thought it is.
So they must have wiggled a little bit to get the galactic center. But I don't think Cosmos is in Russian sky. I think Cosmos is still covered in the German sky.
I thought that was the trade.
The trade?
The whole center was they traded Cosmos or something.
Okay.
That was like a decade ago, so I don't know where.
Okay, but I think the German sky includes the galactic center, which is good because we're interested in the galactic center.
So another follow-up about eROSITA. Did you have simultaneous observation with eROSITA for reverberation mapping?
Right before, conflict happened. Yeah, so before that, the eROSITA does its thing, and we do our thing. So there are a lot of overlapping light curves, which I will mention in one slide later. All right, how are we doing on time? Half, okay, good. All right, I may go light on this. So this is basically the depth and area of the eROSITA survey in comparison with all the other X-ray surveys in the soft X-ray band, 0.5 to 2 keV. So ERAS-8, that's the depth of the final eROSITA mission. So that's 8 scans of the entire sky. Right now, they are stopped at ERAS-3. I think ERAS-3. So that's the first 1.5 years. So one scan takes 6 months, one season. So ERAS-3 is the first 1.5 years of observations of eROSITA satellite. But still, in terms of the area and depth combination, eROSITA survey is still, one of the best, the latest catalog that it will produce. The optical spectroscopy will provide source classification, redshifts, and also the evolution physical property like black hole mass attendant ratios for those X-ray emitting AGNs. And there will also be optical spectroscopy for about 10,000 X-ray emitting clusters of galaxies for cluster size and cosmology studies. The Milky Way Mapper actually also have their hands in the eROSITA stellar components. So they're also going to be using optical spectroscopy to study X-ray emitting CVs and other compacting binaries, flaring stars, and transients, and more. So let's see. So the mesh of those different programs is that for those wide area programs like the eROSITA follow-up and for the repeated spectroscopy of quasars, we try to optimize the survey by merging the different target categories. So each point in here, there are almost an impossible merge of programs across those two different mappers, Milky Way Mapper and Black Hole Mapper. Some fibers are observing stars, bright stars in the near infrared. Some fibers are observing X-ray eROSITA sources in the optical. And some fibers are observing for repeated spectroscopy of quasars. And you can imagine these different programs require different cadences, right? So you have to optimize, you have to take all those different targeting categories, like 50 different targeting categories, and put them on a unified observing plan, like when to observe which field, which pointing, and how to optimize the fiber allocation, and how to maximize the required cadence for those different programs. So it's not a simple problem to solve. This is why once you say, hey, can you also observe this object just turned on yesterday, they will be very mad because you're gonna disrupting their schedule and they have to run simulations, etc. So when things becomes calm, then we can make those troubles, but not at the beginning of the survey. All right, so let's see. What else should I mention here? No. The concept of reverberation mapping is basically you're not resolving the broadband region, you're observing the light echo from the response of the broadband emission to the driving variability from the accretion disk. And that response, that time delay measures the physical size of the broadband region. So you know how big those broadband regions are, and then you have the width of those broad emission lines, and combine width with size, you get the black hole mass measurements. So that's the basic idea of reverberation mapping, but then it requires spectroscopy monitoring to measure the line flux in response to the continuum changes measured from photometry. All right, so the reverberation mapping fields are different. You can think of them as repeatedly visited specific fields, which will build this long-term monitoring of thousands of quasars with optical spectroscopy. So there are primary five reverberation mapping fields in Sloan 5, and we've chosen those fields so that they largely coincide with some of the most famous extragalactic fields, and some of them will also be continue to be observed by LSST and other surveys. So like you can see the cosmos, the XM large-scale structure field, the channel dB field south, and one particular field here, the SCVZ, that stands for Southern Continuous Viewing Zone field. It's the same as the South Elliptical Pole field. So it's pointing at the Southern Elliptical Pole. So why is that pointing special? I will show that in just a minute. Oh, actually here. This is a pointing where space satellites for WISE, for the WISE infrared mission and for the eROSITA X-ray mission, they can continuously monitor that field without any interruptions, because every time when the telescope is spinning to cover different sky area, the axis, there's always a pointing towards the ecliptic pole, okay? And this ecliptic pole is also the continuous viewing zone for JWST, the continuous viewing zone for TESS, the continuous viewing zone for HST. So there's a lot of good science to be done in that continuous viewing zone, where you have very high cadence eROSITA monitoring daily without interruptions throughout the seasons. So that is a primary field that we want to observe with optical spectroscopy, spectroscopic monitoring, as well as our own optical photometry monitoring in these fields. All right, the last thing to mention is the field epoch spectroscopy to understand radical changes in the accretion luminosity from quasars and AGNs. So if you are familiar with quasar light curves, then they vary stochastically. For a small fraction of those quasars, the variability can be very high, can be well over several magnitudes over multi-year timescales. So those extreme variability events are not very well understood yet. And we want to first build a very large sample of such rare events and to understand the physical origins. So this field epoch spectroscopy, the wide field, which overlap well with the German sky of the eROSITA observations, will take 2 to 3 epochs throughout the entire Sloan 5. But they also have a medium tier where for 300 square degrees, you can observe 12 epochs throughout 5 years to get a higher sampling of the spectroscopic variability over this smaller area and only for 2,000 quasars. So the current status is in the first year, we didn't do that robot thing. There was no time. So SDSS-V started with a traditional plate program. We observed 570 hundreds of plates, each with 500 spectra. And there are about 300K spectra already. But that marks the official end of SDSS plates. So the plates area is done, and ask them for a plate until they last, when they are still last, okay? Because all the plates are gone. Once they're all gone, then you're no longer able to get a plate. So we're now in year 2, actually past year 2. So year 2, we did a commissioning at the APO site with the fiber positioner, robotic fiber positioner. We had a lot of issues with the fiber centroiding. The robots were not very good initially to point to the right targets. We're suffering a huge fiber throughput loss due to the incorrect positioning of the robots. But then the team spent a lot of time, the commissioning team spent a lot of time to figure out the technical issues. And now we can achieve similar throughput as the plate program. So for plates, it's simple, you just drill holes. And robots, you have to make the robots to go right where they were intended to go. So around June this year, then finally the fiber positioning issue was completely solved at APO. And then immediately followed by summer shutdown of the APO due to the weather. And, but the survey is operating again at APO just since the beginning of the fall semester. Now, right now, we're commissioning the robotic fiber positioner at the LCO site. So you have to go through that process again. It's a different telescope, and there are different issues, technical issues. And hopefully we can solve all the commissioning issues in the next several weeks. Okay, so that's the current status of the observations. But we already got a lot of data, and the first batch of science papers will be out. Well, some of them are already out, but it will be out in the next few months. And that's just a pretty view of all the robots lighting up on the focal plane. And just to show you, all of them are working. Some of them are broken, they get replaced. All right, in the next 20 minutes, I want to highlight some work we have been doing in the meantime. So now we're going to switch to optical photometry, or photometry in general. So in order to measure reverberation mapping lags, you also need the continuum light curve from the accretion disk. And we observe the continuum emission using optical imaging. And we're using the DECam imager, the same instrument we use for the dark energy survey. It's a long-term program. It runs from 2019 to 2023 with a 3-day cadence in several bands, GRI, for all the BHM arm fields that are accessible from the CTIO, the site of the DECam. So you need observer every 3 days. It's quite a lot. We did this kind of in solo mode in the first semester of 2019. But then a lot more teams proposed time domain monitoring programs. So led by Rest and Gotham here, we put together all the programs called DECat. I forgot what that stands for, but it's definitely not a cat. But it's an alliance to.
Alliance for transients.
Yeah, it's DECam alignment for trends. So lots of the time domain high cadence and medium cadence programs are put together to pool observers from those different teams. Each contributor maybe several nights through the semester. And this has been going on for a while, and I think it sets a good example of the DECam, of this kind of program, and I'm pretty sure that it's going to last, even when LSST kind of slowly starts. So our DECam data management is done here at NCSA. Thanks to Monica, Robert, and Doc for spearheading all those reduction stuff. We also have students and postdocs to analyze, to compile those image data. So as of today, recent weeks, we have mostly stabilized the source catalog constructions and light curve constructions, and we'll be able to have them ready in a few weeks for internal uses. So that's something that Gotham and Decker, we should talk. Hopefully by the end of this semester, where to access the data and how we're going to make this more useful to Illinois researchers. So this data, they are not officially SDSS-V products, not yet. That means we have a say in who can use the data. And my intention is that Shen is also has her own program with different fields. But my intention is that if someone here has a good idea to use those light curves, let's talk. I'm happy to share the data with you. For long-term archiving and distribution of the data set, we're running into a bottleneck because clearly we need lots of web space and computing resources. So if there's something that CAPS is interested to host this data product, we can also be happy to have a discussion later. Because this is going to be a legacy data set for the entire astronomical community. SST is going to monitor those fields. A lot of those are LSST deep drilling fields. And some of them are Euclid deep fields. So there's a lot of synergy to talk about here.
Wouldn't more labs host that because it's deep?
They have their own kind of infrastructure. The OR lab, data lab, they reduce all those DECam images, which is separate from the DES collaboration reduction, separate from the DECal reduction, and separate from our NCSA decade reduction, if I'm correct. But the OR lab only deals with public data, so some of them are still not public yet. Anyways, lots of data already. For a single field, we have millions of sources, hundreds of epochs in multiple bands, and single epoch depth is pretty good, 22 megatune. I have an example of light curve.
Quick add-on here, just in case Joaquin's not aware. So NOAA lab will only process the data up to flat fielding registration, but not doing any difference imaging at all.
Right, but if we give them, or if people give them processed data to host the community.
They can do that, but NOAA lab will be announcing next semester a large survey call for programs. This is not the long-term status, this is the 5-year and beyond. And we've been talking about potentially asking for a large chunk of DECam time during LSST operations. I think it would make sense for the Center for Astrophysical Surveys to take the lead in processing such survey data and hosting it here at CSA.
Something that I'm not very super clear about is the decade of infrastructure. I'm not sure if anybody here from NCSA are familiar with.
The question was that it's DESDEM, just it's the DESDEM.
But it's not just the DES, right? It's also DESDEM, yeah.
It is not just DESDEM. It is also being held up by a grant that's working on shears over the full sky, or as much of the galactic skies you can, extragalactic skies.
What's the infrastructure doing it? And it's the DESDEM infrastructure, right?
Oh, yeah, sorry, yeah, the infrastructure, but also the kind of content and the scope of decade. So what is decade going to do? It's going to take all the DECam programs and uniformly process them and archive the data products somewhere for the community.
It is I would saying it's for the community is, I mean, it could be. I think they have to talk to the Delve group to basically get access.
Right.
And it is not all observations. It is all observations that are above the galactic plane by a certain distance. It's something like B of 20 or something like that.
Right. So my understanding is that our DECam imaging is reduced under the umbrella of decade, but we're still kind of hidden in the shadow, right? I mean, there's no obligation for us to give the data to anybody unless there's some formal or informal agreement.
Yeah.
The Delve collaboration basically is the thing that's the gatekeeper for access there, and they say that anybody that wants to join them can have access to the data. I have nothing that is keeping anyone away from that data if they are a member of that group. There is no gatekeeper beyond that.
Right. Anyway,
It's not automatically public. I think that's what it is.
Yeah, right. That's right. But Delve has been taking data and making public releases, which are then going to NOAO, and so they are being served that way through as a catalog, I believe.
I can send you a more complete list of the fields later. Yeah, it's quite complicated because when we co-observe with different teams, sometimes another group also wants to monitor the same field, but we set different parameters. And then we say, okay, since we're monitoring the same field, let's just share our time. So those observations will be put on a different program ID, proposed ID. Okay, and the data status will also be different. Sometimes, let's see, the field name slightly changed, the coordinate slightly changed. So I'll give you a full list of all those details that I'm keeping tracking of, so you can grab all those the fields. But as I say, in a few weeks or maybe a few months, we hope to establish this database here, so you can easily access them instead of copying all those huge of, millions of exposures.
See if it hits any SPT data, because I think that one looks like it just barely misses everything we've ever observed. But just barely.
Do you observe the south ecliptic pole? No, right?
Right. Almost.
Almost. Okay, too bad. All right, so let's so an example light curve in the SEP field, southern ecliptic pole. So in the last 10 minutes, 5 minutes-ish, I just want to showcase some of the planned work, relevance, why we're gonna do this all imaging surveys. So one thing you can do is to do a quasar selection. So my former postdoc, Chen Yang, who is now a CFA postdoc fellow, did this work, published, accepted. If you combine all those deep optical imaging, photometry, multi-band photometry with near-infrared photometry from various public surveys and WISE and Gaia, you had a pretty good sky coverage. So we were able to use the DS 5,000 square degree DR2 release to select a photometric quasar sample within that red footprint. Now, with the inclusion of near-infrared data, the photometric redshifts, photosys, for those quasars and galaxies is actually pretty good. We have comparison with the spectroscopic disease, and at least I'm pretty satisfied with the performance of the photosys algorithm that Chen developed. So one last slide before I stop. Is again going back to the multi-wavelength synergy angle. When we have those photometry, optical, and WISE light curves and X-ray, eROSITA X-ray light curves, and we can observe variability across a very wide, broad wavelength range. So here's one example you can do with my current postdoc, Jun Yao. This is one source in the southern CBZ, in the south ecliptic pole field. As I mentioned, WISE also has a very high cadence coverage there. So the red points here, each point here is a WISE detection. Okay, so there are more than tens of thousands of data points over 12 years. Same way as the eROSITA satellite is continuously covering the south ecliptic pole. WISE does the same thing. And the top is an AGN, bottom is a constant source, might be a constant star. But if you zoom in small regions, then the light curves are sampled at hourly cadences. So that's pretty good, infrared. And then we also have optical light curves, so you can measure variability for any source you want in those fields. This is just the structural function, so let's measure the IMS variability of AGNs. For optical in the green, in the blue, and for the WISE mid-infrared in the orange. So it's very well considered. This is an ensemble variability structure function, but important thing here is that for the same population of quasars, you see that the variability structure function has different shapes between the optical and in the mid-infrared, and different normalization. So that can actually allow you to tell the geometry of the torus. So we're gonna write up something on this angle. So I'll stop here, and I hope we can have some additional discussion today or later, how we can best use this data set.
How do you get the geometry of the torus?
Right. I'm happy to explain here. So that's the black hole. The optical emission comes from a black hole. The infrared response comes from the torus. Now, if the torus if the geometry is purely phase-on, then the response in the infrared light curve would be a shifted light curve of the optical. But there's no geometrical dilution. The transfer function is a delta function. It's a pure shift of the light curve modulated by some emissivity scaling, okay? So in that case, the structure function would have the same slope.
Yeah.
However, if this torus is tilted, then the near side would have shorter legs. That would have longer legs. In technical jargon, the transfer function is not a delta function.
Yeah.
So it will smear out variability to make this slope steeper. So you can actually do analysis to figure out how big is the size of that torus and what is the inclination angle. So without any measurement of the lag whatsoever. So this is based on statistical properties of the variability, which is the easiest thing you can measure with structure functions. Now we have the data, the right data to do this kind of measurements.
Let's thank our speaker and do the question.
Thank you. When you talk about quasars which change variability on large scales, is it somehow related to changing look AGNs? And you said something about how spectroscopy and photometry changes in optics, but do we know how it changes in X-ray? I mean, for these changing quasars. Thank you.
So I don't get the final part. What's the X-ray angle here?
The question, do we know how X-ray flux changes on these large scales for the same objects?
You mean time scales?
For this 10-year?
Yeah. They are more variable in the X-rays, actually. So you can observe very large X-ray variability on much shorter time scales, because the region is so much more compact compared to the accretion disk and the broader region. But for the optical, for the accretion disk to change that dramatically, it's hard. The viscous time is hundreds of years. So that accretion disk is...
Say that it is a low limit 100 years. It is for ultraviolet probably region, yes, or for...
But the optical is also changing. It's not just the UV, but the optical emission is also changing rapidly, not dramatically, like by 2 magnitudes over 5 years, which is strange because the optical emission comes from larger radii, and the viscous time there is too long for them to change that dramatically. Basically, completely shuts down the accretion. So something to think about, which does not yet have a clear answer.
Any other questions, or is that?
So for so is that related to the dusty torus like viewing angle? So if like it's due to the viewing angle, should we expect to see more like obscure AGN if they have a similar structure function because it's phase on?
Yeah, so if a pure phase on, then you shouldn't observe any smearing effect. So the power spectrum or the structure function should have the same slope.
Right.
But as long as it's slightly tilted, then you would have a broader transfer function to give you that smearing. So that's why you're seeing that this slope you have suppressing of short time scale power of variability.
Right.
It cannot go all the way to edge on. Then it's going to go on. But at least it can tell you what would be the distribution of orientation for type 1 AGNs.
Okay.
And that's typical. It's a very good measurement, because I don't think we have a definite measurement of the orientation. We only know that it's 45 degrees, 30 degrees. But now let's measure the orientation distribution.
Okay, and also like, do we expect to see more jet because it's like face on?
That's a great question. So once we know the orientation in a statistical fashion, yes, let's talk about the morphology of the jet and how that falls into this entire this overall picture.
Yeah, and alignment with the galactic rotation curve and all that.
I guess. Also, if I recall correctly, there's not much correlation between the small scale orientation and the large scale orientation.
There's not a lot of data either, right?
There are not a lot of data that I'm aware of, but I'm very ignorant in that field.
Yeah. Going back to kind of what Gil was asking, so in the south,
Yeah.
is there like in DES for galaxies, is there an I-band limit above which you will be complete for spectroscopy?
Yeah, so we target.
The first or second slide where you had
It's not this one, right?
no, very like the first or second slide.
This one?
Next one. No, you had the table.
Oh, table. Sorry, table. Yeah.
So is everything less than 20 going to be observed?
No.
Okay.
Only if they are BHM targets.
Yeah.
So that's mostly X-ray agent and broadline agent in the BHM mapping fields.
Okay. And then my last question was, there were 3 Illinois faculty members on this. Could you just say briefly what everybody was actually doing on SDSS-V?
Yeah. So Tony is part of the LVM, the local volume mapper. They just had a meeting finished yesterday. So Tony was there for the kickoff of the local volume mappers. So Tony does a lot of IFU observations and galactic kinematic stuff. So Shen is interested in the BHM. For example, the field epoch program. And I'm interested in reversion mapping and also general BHM and X-ray. I really want to get my hands on the X-ray data. So we're collaborating with the MPE on the X-ray stuff, multi-wavelength synergy stuff. So that's for the three faculty members here. Each faculty slot contains an unlimited number of students, but only one member for postdocs. And a full institution member covers everybody. And I am assuming it's covering the entire university. So it's not just astronomy, but also NCSA and physics. And it's not much more money, a lot more money compared to an associate member.
Oh, I thought it was double. It's not double?
It's double.
Oh.
But with $500,000, you get 3 slots. But now you have unlimited slots. And maybe we can get a discount because it's already like 2 years into the survey. Yeah. Just don't buy it like until the last year.
We're doing for the young supernova experiment. We're coordinating people joining in now, and then just extending the survey, so it keeps overlapping more with LSST.
But I think it will be done with the 2.5 meters at that time. I mean, I'd be surprised to see if they're going to push this for another 5 years after 2025. The 2.5 meter, dude. I mean, this is a tiny. Yeah. But again, if you know, I know that DECa and you can use the optical spectroscopy. So they kind of the additional faculty interest in the department, I think. So we just need to find another 10 hundreds of K, right?
Any final questions?
Thank you.